Okay, today we have another seminar from USACM student chapter. And as usual, please try, for those who are already in the audience and for those who are gonna watch this in offline mode, please join our Discord and YouTube channel. Hopefully you will find some related and good information about computational mechanics. And if you have any question, please try to reach out to us with this email here. And as I mentioned, in those channels, there are a way that people can talk to each other and communicate. And today is my great pleasure to introduce Dr. Yakov Zelkiman from Johns Hopkins University, and he's gonna share their interesting work on leveraging structural optimization for more efficient, sustainable, and economical structures.
Okay, so first I want to say thank you for inviting me to give this talk. And second, I want to thank who made it here and joined the talk. So the title is indeed Leveraging Structural Optimization for more efficient, sustainable, and economical structures. And the plan for today is a few slides on motivation. Then I'll have short introductory class on structural optimization, followed by 3 examples of how we can use it to improve our structures, and finally some concluding remarks. So buildings are responsible for about 6 to 8% of the global CO2 emissions. And when we combine it with the fact that by 2050, the population of Earth will reach 10 billion people, and just to put it in perspective, it's about another United States every 5 years. So all this together, what it tells me is that we need to reduce the amount of concrete or amount of structural materials we use in our structures. The other side of it is us, the engineers, the academic people, and our intuition is not as good as we think it is. And let me ask you this. So if you have this floor plan, and here you have kind of some columns around and a core wall, and I ask you, where would you want to add this new column? Is it would be point A, B, C, or D? And actually, you can scan this QR code and put your answer there. Maybe I can wait 15 seconds for you to do this. Very simple, just scan, pick the one, and just interesting to see what you would think. Okay. So this is the optimal location. But what we really see here is 3 layers of information. The first layer is the colored pixels, where the color in each pixel represents the required thickness of the slab if the column was located at this location. So for example, if the column is located anywhere in the red region, it means that the thickness of the slab should be around 30 centimeters, and so on. And you can see that the optimal location is somewhere around point C. The another layer of information is the black crosses, which are responses I got from engineers that I asked them the same question, and they all kind of missed the optimal location, but put it in perfectly reasonable and intuitive location. The last layer is the gray square at the center of this blue eye, which represents the optimal location of the column, and this gray square is obtained by formal optimization. So what we see here is 2 things. The first is that our intuition, or intuition of engineers generally, is not as good as we think. We miss the optimal location. but also at the same time, we see that formal optimization managed to find it. So really, optimization is a very powerful tool that can help us to escape this trap of our intuition. And maybe I just emphasize, it's not that I'm saying that our intuition is not important. To the contrary, our intuition is very important to be judgmental and critical of whatever that we do. We just need to be aware of its limitations. Okay, so what's topology optimization? What's structural optimization? Basically, it's a design approach that takes manual design process and convert it into a formal constraint minimization problem, and then solve it with programming tools. It can be divided into three components. The first one is the design variables that represent the parameters that we want to change, or want to optimize to change or to tell us what to do with them. The second one is the objective function, and this represents what is the goal of optimization, what we try to improve, what performance can be mass, cost, CO2 emissions, and so on. The other component is inequality constraints, usually represents different different performance measures, or sometimes different constraints on the design space. And finally, we have the equality constraints that often they are just the equilibrium constraints that, of course, has to be satisfied. Another terminology I want to introduce is parameterization, which is basically the way we relate our design variables to the structural features. Or in other words, how the mathematical variables related to the physical real features that you want to change. I use gradient-based algorithms, and their advantage is that they are very efficient in dealing with large problems. On the downside, they require more computations, more derivations, and so on. If we look at the most general 20,000 feet algorithm for optimization, this is how it looks. So we begin with some kind of I go from left to right. So we begin with initialization of our design parameters, and then we use finite elements to assess the performance, followed by sensitivity analysis, which we'll talk about in a moment. Update the design, check for convergence. If it's not, we do all the cycle again. If it's converged, we completed the process. So the finite elements are used to solve the state equations, and of course this can represent any physics, statics, thermal problems, fluid, you name it. It can be linear, non-linear, as long as it has partial differential equations that represent it, we can solve it, or we can solve it with finite elements. This means this can be embedded into this sequence. Another thing I want to talk about is sensitivity analysis, which is basically tells us how the design parameters affect, or change in the design parameters affects the structural response that we care about. And usually it can be fairly complicated, but fortunately there is so-called the joint method to compute this. And the important thing to know about it is that in order to compute our sensitivity analysis, after we derived all the expressions, which is a challenge of itself, but once we have all the expressions derived, it takes basically another solution of the state equations in terms of the computational cost. Okay, so going back to our problem, we want to reduce the amount of materials that we use in our structures. And if you look at the distribution of, in this case, concrete in concrete structures, we see that the vast majority of the concrete is located at the floors. So really, if you want to have the maximal impact, we should try to reduce the floor mass, and even more so, this will reduce the force that has to be carried by the foundation, beams, and columns, so to have more savings to it. Okay, so the first example I want to share with you is optimization of support. So we already kind of looked at an example of it, but now we want to take a closer look at how it works and so on. Yeah, so this is just three requirements I want for this optimization. I want to be rich design space in the sense that I want the columns to be able to move freely across the entire domain. I want it to be numerically efficient, and I want to be able to embed architectural and other constraints. So the first thing, the finite element model, and here the finite element model represents the floor, and therefore the model with Mindlin plate elements, well-known element. I just want to put it out there. We use Mindlin plate elements, but of course we implement them ourselves in-house. And the reason for this is that we must have access to the formulation in order to get the sensitivities and so on. Next, once we have the model of the plate, we want to parameterize our supports that can move freely in the entire area of the floor. And the problem there is that if we connect them to nodes, what happened every iteration, we might need to remesh the floor, which is computationally expensive, or will be restricted to very small changes in a design. In order to resolve those issues, what I came up with is so-called the stiffness projection method, where essentially I detach the supports from the plates, and this is done by taking the stiffness of the column and simply projecting it on some small area around the current location of the column. Of course, we want to still maintain the differentiability of the method, and therefore what we really do, we use some kind of a super Gaussian projection, which basically what it does, effectively it projects on a small predefined area the stiffness, but mathematically it projects on the entire domain, and hence preserves the differentiability of this projection. And then once we have the projected stiffnesses, we assemble the global stiffness matrix in a standard fashion. Moving on to the formulation itself. So first we minimize the floor volume, and the design variables are the coordinates of the columns and the thickness of the floor. So basically what we ask ourselves is where to locate the columns and what would be the corresponding floor thickness, such that we minimize the floor, and we have a bunch of constraints. The first constraint is deflection constraint. Basically, we don't want the deflection at each point to be greater than something. Just to mention, this fairly complicated constraint in the context of the column optimization, because the allowed deflection is defined by the span or the bay length at each point. But because the columns constantly change the location throughout the optimization, it's not trivial how to define this allowed deflection. We eventually ended up defining it as a function to the closest column, and then of course we get smooth and differentiable representation. Another point I want to make here is that we need to ensure that the deflection at each and every point will be less than allowed deflection. Since we don't want to have a constraint for single point, what we're actually doing is we are constraining the maximal deflection or the maximal relative deflection. However, since max operation is not differentiable, we replace it with a differentiable soft maximum, specifically a p-norm function. And this kind of aggregation procedure is often implemented where we have local constraints to consider. Other two constraints are shear stress and bending moment constraints, which I'll not go into, but they both have a local nature and therefore aggregated constraints. And finally, we have the equilibrium equations. And this is how it looks. This is a very simple example that we use to verify our method. And indeed, the optimizer managed to find the optimal location of the supports. But looking on a more interesting example, this is a structure from San Francisco, and we wanted to see how good can we do there. So the first thing was, what you see here is the floor plan, simplified floor plan, where we kept the location of the columns as was designed by the engineer and kept the partitioning walls of the floor. So first thing we did, we did analysis of this floor, and we see that the volume of the floor is 285 cubic meters, and the plot that you see here is the relative deflection. So it means that the value of 1 means that the actual deflection equals to the allowed deflection at this point, and 0 or blue regions represent cases where the actual deflection is much smaller than the allowed deflection at these points, and hence indicates poor utilization of the feasible space. And then you see, okay, let's let the optimization to do its thing. And first, we allow the columns to move only along the partitioning walls, and therefore this change in the design does not change anything in terms of the performance or the service or architectural service of this floor. And we see that even with this very restricted free optimization, we get 18% savings in concrete, in concrete, and also we see that more regions of the floor actually reach their allowed deflection, indicating better utilization of the material. And again, just to mention, we minimize for the volume, and we use the relative deflection as a proxy or as a measure of the effectiveness of the floor. Next, we release these constraints, allow the optimizer to move the column freely, and sure enough, we got much better results with 44% reduction in concrete volume, and most of the points actually reach the allowed deflection there. So we see that if we increase the freedom of optimization, we get more and more savings. Having another example that's showing that the aim of it is to show again the trade-off between the freedom of the optimization, which is represented here by the horizontal axis, delta max, which is basically we had on the left side. So if I look at this design, this is a reference design made by engineers, and I ask myself if I allow the optimizer to move by a delta max from the reference design, how the performance will improve as with the increase in this freedom. And again, we see here that most of the gains, and the vertical axis is the volume of the concrete, and we see that most of the gains are obtained for small increase in the freedom. So for delta max equal 2, we really get most of the savings. What it tells me is that we don't need to do much, or we don't need to pay a lot in terms of architectural performance to get a significant savings in the concrete. Okay. So the second example is once we have the columns in their place, the next question to ask, okay, what would be the thickness distribution of the floor? And here the main question is constructability. So how to do it in a way that this can be constructed? And when I think about constructability, I think that the design should be made of straight lines, because this will make the formwork fairly simple and the installation of the reinforcing bars and so on. So we want to define our optimization in a way that will ensure that the optimized design will be made only of straight lines. And the way I came up with is just to say that we can represent any polygon as overlap of different rectangles. But before that, we need to talk about how we model it. So as I mentioned, we use plate elements, but is it accurate to model a slab or floors with different thicknesses with plate elements? I'm not sure, because there's assumption there that there's instant transition of the stiffness, but really it's not the case, because this region here really does not have any strains there. Maybe more accurately is to have some kind of effective thickness that kind of removes this this corner that does not really work. And to test this hypothesis, we kind of came up with this simple beam, and we want to investigate this and want to compare the ground truth response that we will obtain by modeling with plane stress elements with a model that made out of beam elements with a varying thickness of the beam, representing this inset value of the effective thickness. And of course, This is not really what we're doing in this work, because we deal with plate elements, not beam elements, but there is equivalency between beam and plate elements with respect to plane stress and solid elements. And this equivalency, and this is why we think that this investigation is a valid investigation also in our case. So for a specific case, if we have this length being 40% of the total length, what we see here is three curves. The dashed curve is the reference curve that's obtained with plane stress elements and considered to be the ground truth. The red curve is the deflection curve obtained if we look at the real thickness of the beams. And we see indeed the deflections are smaller, representing this overestimation of the stiffness. However, for instead of 0.7, the thickness difference, we get very accurate, fairly good agreement with the ground truth. And then we increased this investigation to a whole range of parameters, and also included different geometries of beams. And we saw that actually the 0.7 inset is really gives us a good agreement. So this is a way that we can reliably model plates with different thicknesses using plate elements and not expensive solid elements. All right, so we have our parameterization based off 6 parameters: the size, the thickness, the angle, and so on of the draw panels. And now we want to project them or change our mesh, or change our model to account for this. So yeah, so what we did here is so first it is projection on the finite element, and bunch of different operations, and gives us the thickness distribution that is function of our mathematical parameters of the draw panels. Moving on to the formulation, again, we have minimized the volume with bunch of constraints, very similar to what we had before, with the difference that we add this complexity term that kind of penalizes more complicated structures. So there's gamma, this measure of the complexity, and alpha is a weight assigned to it. And the question is how we measure the complexity. We said the complexity is related to the total length of this thicker regions, and again has to do with the fact that many of the much of the work is related to this thicker boundaries. So looking at this example, only now I optimize the thickness, and what we'll see here is for different values of alpha, for different values of alpha, you see here the optimized design, and as alpha increase, as alpha decrease, you see that they get more complicated designs in a sense that we have longer boundaries. And yeah, let's let it finish, and then when I plot everything on this graph, again, the horizontal axis is the complexity, the vertical axis is the volume savings, and again, we see that most of the savings obtained before we reach the maximal complexity. So small change in complexity gives us a lot of savings. Another example I want to show just real quick, what we saw in this example is that the optimizer actually uses not only the stiffness of the concrete, but also the mass of the stiffness to increase its efficiency. So again, we see that the optimizer teaches us something about the system. The last example I want to show is a optimization of the layout of the post-tensioning cables. And again, once we have the column set and the thickness set, now we go and optimize the post-tensioning cables. And the parameterization here of the cables is based off B-splines, because they're very nice curves, very easy to enrich and control, and so on. And the first thing we need to do, we need to have an analytical expression for the forces that the cable applies on the floor as function of its shape, which will allow us to utilize more different shapes of the cables for our advantage. Again, the formulation here is very complicated, but what I really want to emphasize here is F3 and F4. Those are constraints that limits the curvature of the cables. And for example, the F3 is limits, instead of limiting explicitly the curvature, which is really impossible, we take advantage of the B-spline representation, and basically what we do, we limit the angle or all the angles of the control polygon, and this way we get implicit control of the curvature of the cables. On this very simple example, this is a reference design where we have distributed cables in one direction and banded cables in other direction. This is the classical design of PT, and as I increase the freedom of the optimization, we see that we get more and more savings and more complicated designs. So again, as we saw throughout, more freedom to the optimization give us more savings. And then we saw something kind of strange. We saw that the cables can avoid of going above the column, which is kind of counterintuitive. Usually, we do want the cables to move above, reduce the punching shear effect, and so on. But then when we thought about it more, what's happening here is that the cables kind of pass on the top face, but also apply clamping stress on this face, reducing much more efficiently the tensile stresses there. So again, this is a case where the optimizer or the optimized design teaches something about the performance or about the systems that we optimize. And another unexpected thing we saw in the layout of the cables around the edges, not going to it now. And lastly, I want to mention this slide, where again I show on the horizontal axis the complexity, on the vertical axis the cable weight or the amount of material. And again, the same trade-off is present where most of the savings are obtained for small increase in complexity. And yeah, so basically we can gain a lot, not with a lot of changes to our design. So if I'll conclude, I want to conclude with several points. First, our intuition is not as good as we hope it is. Again, not to say it's not important. The intuition is a super important tool that we have, but sometimes it also puts us in a trap in a sense that explore different new designs. Structural optimization is a very powerful tool that can allow us to escape this trap and explore different new unexpected designs, and therefore to lead to increased efficiency of our structures. Fortunately, in most cases, we don't need to change much traditional designs to get a lot of savings. And for me, the most interesting part is the fact that the optimized designs can teach us about the system being optimized and often reveal truths that we didn't know before that. And this is very super interesting. And lastly, I want to say that really anything in any system can be optimized as long we can represent it as a bunch of functions. And with this, I'll finish and answer any questions if you have. Yeah, thank you.
Thank you, Yakov. Very interesting presentation. So we first start with like the audience. If anyone has any question, please raise hand. Yeah, Rajwal, go ahead, unmute and please ask your question.
Hi, Yakov. Thank you so much for this wonderful presentation. I had a quick question. Like, you were optimizing many of these, like column spacings and cost and deflections, all those constraints you had. Like, did you also consider, say, for example, architectural constraints? Like, for example, you do not want to have columns in the middle of a hall or something like that, or in the middle of a floor or something like that. Means, like, did you consider that, or like, how can this be considered in general?
Yeah, definitely. Sure. Again, so I lost for some reason. So Do you see the screen?
Yeah.
So if I go here, for example,
Mhm.
so if we look at this design, so this is basically I limited the design space in a way that the columns are restricted to move only along the walls or the positioning walls. This is, in a sense, this is an architectural constraints. So I limit the design space to impose architectural constraints. Another example for this is also here. Here, basically, I have this box around every column here that tells me what is the allowed range for the column, and this implicitly or explicitly represents some architectural constraints. The point is because the parameterization is very explicit, so the design parameters are the coordinates of the columns. This means that I can easily embed any geometrical constraint on the allowed or forbidden regions of the columns. Yeah, I guess more complicated architectural constraints related, I know, to connectivity, light, air quality will need more thought.
Yeah. Thank you so much.
Yeah, thank you.
Hi, Yakov. Hi, I have hi, Yakov. Thank you for your very cool presentation. I like your plots to show how changing the location of the columns will reduce the volume and also show the change of the contour. So I have a quick question.
Do you mean this one?
Yeah, the previous slide that you just showed, and
Okay,
yeah,
go ahead.
yeah. I have a question regarding so the first one is a very general question. So you use the volume as the objective and constrain the deflection in your optimization model. So have you tried like minimizing the deflection and constrain the volume fraction like what we typically do in topology optimization? So can you tell me why do you use minimizing volume fraction as a yeah.
So it's a great question, Chuan. And the answer is because in structural engineering, usually we have some kind of required performance, right? So we want the deflections to be less than something in order to comply with regulations and codes. And there is no benefit, or usually there's no benefit in outperforming this. So basically, I want to use the least possible material while ensuring that I still within the allowed ranges.
Okay, gotcha. Yeah, but I think your method is general and it will apply to like minimizing the deflection while constraining the volume fraction.
Yeah, it's it's always you can change those.
Okay. And from this page slide 28 to 30, I think you have showed the different thickness. I think 3 different thickness for the plate, right?
Let me go there. 28.
Yeah, maybe you. Yeah, here, yeah, this slide. You have shown us 3 different thickness for the different components, right?
Yeah.
So is it also an optimization variable?
Yeah, so I did not have the chance to really go into this, but basically each draw panel has 6 parameters, 2 for its dimensions, A and B, 1 for its thickness, 1 for its orientation, and its location XY. So
Okay.
thickness is also parameter, in many cases, so often I will keep the thickness constant for all drop panels. In this case, I wanted to see the effect of different thicknesses, but generally, if you allow each drop panel to have different thickness, what it is end up being very complicated designs and really kind of misses the point of keeping it simple.
Okay, like it is more challenging to solve the coupled problem, right?
It's just more challenging for realizing to actually building it. It's becoming too complicated.
Okay. And here the thickness design variable is continuous and it's not.
Yes.
Okay, I got you. And one last question is regarding the page 34. You showed us the I think it's like the design domain is symmetric, but the optimized layout is not. Yeah, can you clarify that?
So the design space is not so the problem is symmetric. The optimized design is not completely symmetric, and so I don't know. I cannot explain it exactly, but for starter, I had to give some random perturbation to the initial design because of numerical reasons, and this definitely explains, at least to some extent, the fact that the optimized design is not perfectly symmetrical. But probably there is more to this. Yeah, actually, I'm really bugged with the fact it's not perfectly symmetric. Yeah, I have some thoughts about it. Maybe have more smooth projection of the balance forces. But yeah, it's symmetric, but not perfectly symmetric.
Okay, I see. Yeah, it's more related to technical details, I think.
Yeah, and maybe another point. So what happens? There's the cables can. I start with many cables, and some of them are being removed along optimization. So basically, what can happen is that the optimizer can end up being with an odd number of cables, and this will result in non-symmetric design. So sometimes with integer, if you require the design variables will be integer, you end up with a non-symmetric solution for a symmetric problem, just because your variables are symmetric or are integer. Sorry.
Integer. Okay, I got you. Okay, thank you. And here your design variables, you're using like Bezier curves for the cables?
Yes.
Okay, great. Yeah, very nice presentation. Thank you.
Thanks.
Perfect. Is there any other question? If not, then I have like few questions, not maybe from. This is not my area, so I'm just curious. Yakov, like here, do you optimize for static load or dynamic?
Static load.
Static.
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 Static. Static.
Static. So one row of columns is like for earthquake. Do you think this is gonna change these designs if you consider like dynamics and earthquake?
So I think, and correct me if I'm wrong here, that the structural rigidity or the system that deals with earthquakes are not the columns, really the core walls. Really the walls and maybe frames, but mostly walls. And the columns does not have too much of horizontal stiffness to begin with.
But the main role is that to just transfer the loads to the foundation during the excitation.
But during excitations, you have mostly horizontal acceleration, right? Not only, but mostly. And this horizontal acceleration translated to horizontal forces that then carried by the walls down to the foundations, because the walls has much higher stiffness, much higher horizontal stiffness. Having said this, I think it's super interesting question to see the trade-off, because on the one hand, to maximize the moment of inertia of the columns, you want them to be as far as possible.
Yeah, that's exactly.
But from the fully vertical or static consideration, it will be with small inset inwards. So there's some interesting trade-off there.
Exactly. That was my like thinking. And another question I have is like, do you think, because sometimes I guess sometimes we have some constraint from the foundation design perspective. Do you think we have that kind of flexibility to put column everywhere we want, or there are some constraints from the foundation design?
So again, this is a good question. I didn't think about it, but when I think about it now, I think it's not conceptually from the optimization perspective, it's not very much different than the architectural constraints. Basically, the architectural constraints are geometrical constraints that tells me the columns can be here and cannot be there. So this can represent also foundations or really any other consideration.
I see.
Right?
I see. And the last one is about the freedom for the cable design in 34, slide 34. I'm not familiar with the practical aspect of designing these things. So those really curved thing, is that possible to design? Like, is that possible to generate such a thing, or?
Yes, for sure. For sure.
Oh, like whatever curve people can build.
So basically there's the complexity here, right? The horizontal axis is the complexity. And the way I measure it actually is the total amount of curvature. Again, as a measure of the complexity. And of course, contractors would prefer to have
Exactly.
this design. Oh, damn it. We prefer to have this design with only straight cable. But this means that we'll have 5 kilograms per meter square. If a contractor willing to have more complicated design, it can have much less cables, and depends how much you're willing to go to get less and less cables.
So the complexity is also a kind of constraint in your optimization.
It's in the objective. So basically, this multi-objective optimization, I optimize simultaneously the amount of cables and the complexity, and then I see the trade-off.
And like, just out of curiosity, when it comes to the multi-objective, how do you optimize?
So I talked 10 seconds about this here. So this is the other example of the thickness distribution. When you see here, there's two components to the objectives. The first component, which is basically the volume of the floor. And the other component is the complexity, which has, again, a product of two variables, two entities. The first one, gamma, is a measure of the complexity, and the second is alpha, which is a parameter. Then by optimizing with different values of alpha, you get different weights to the complexity. For higher weights of complexity, I expect to have low complexity, optimizing with low complexity, but with high volume, and vice versa. If I set value alpha with small value, this will promote more complicated designs, but with less material. And you can see it here. This is exactly what you see in this clip, right? So I optimize with different values of alpha, and you get, so I reduce alpha, and the complexity increases.
By the way, this is the non-convex, right?
No, not convex at all. So what you see here, so the color of the bubbles tells you what alpha I was using. So see the low values of alpha, the blue range, end up being in this area that has low volume, but high complexity.
Perfect.
Not
Very
perfect,
interesting.
but okay.
Very interesting. Thank you. Is
All
there
right.
another question? Otherwise, we just thank our presenter. Okay, there is nothing more. Thank you, Yakov. Thanks for your time and very interesting presentation.
Thank you all.
See you.
Bye-bye.
Bye.
Bye bye.